Hey Physics 20s, it's me, Mr. Jukley, here today to talk to you about Unit 5, Lesson 8, Gravitational Field Strength. Now, we've dealt with gravitational field strength a little bit before, but we're going to be taking a bit of a deeper dive into it here today. Pretty exciting, pretty neat stuff. Oh, speaking of 8s, what did the 0 say to the 8? Nice belt. Anyways, if you don't get that one, draw it out. Okay, so first thing that I actually want to go through and talk about today is, remember Henry Cavendish from last lesson? Figured out the gravitational constant, verified Einstein's predictions about the inverse square law and the effect of mass on gravity, or force of gravity, I should say. Yep, Cavendish was actually able to determine the mass of the Earth. You might want to put the video on pause and think about that for a second. How do you figure out the mass of the Earth? It's not like you can put it on an electronic balance. That's not going to work out so well for us. Something that's flying through space at a ridiculously fast speed. How do you figure out the mass? Well, all starts with that gravitational constant, g. So remember, he used the torsion balance to figure out g. Once we figure out g, well, if I want to figure out the force of gravity between any two objects, well, we can measure that, right? Especially if it's here on Earth, and especially it's the force of gravity between Earth and one other object. So essentially what he did was he chose, realistically, any object. We knew at that point the radius of the Earth, and I actually had to look into how a person could figure out the radius of the Earth. There's some pretty simple ways that you can get a really good estimate of the radius of the Earth. All right, so we're using the radius of the Earth, and we're looking for the mass. So if we have the force of gravity, we have the gravitational constant, we have another mass, and if we have the radius of the Earth, we should be able to figure out the mass of the Earth, which is pretty amazing, pretty simple and pretty amazing. So we want to start by talking a little bit about force of gravity, right? So force of gravity is the attraction that, and this is the one that we talk about for the most part, is between this person and the Earth. One thing that we talk about a little bit less is, if say that's an 800 Newton person, the person is being pulled towards the Earth with a force of 800 newtons, but guess what? The Earth is also being pulled towards the person with an equal but opposite force, also 800 newtons, in this case, upwards, which is pretty neat. Cool. So when we're talking about this force of gravity, remember that there are two ways to calculate the weight or the force of gravity in an object. So we've got the universal law of gravitation, where we're dealing with Fg is equal to g m1 m2 over r squared. But if we're thinking about the weight of a person here on the surface of the Earth, well, realistically, the radius is just the radius of the Earth, right? Because the person is standing on the surface of the Earth, and honestly, it doesn't matter where the person is standing. It's pretty much exactly the same everywhere. I know you might be thinking to yourself, oh, aren't there like crazy tall mountains and like crazy deep trenches on the Earth? And I mean, from our perspective, yes, but when you back it up a little bit and you look at that blue marble that's flying through the universe, it's pretty much perfectly round. A kilometer or two here or there isn't going to make a ton of difference, right? If it's something, I believe it's something like 12,000 kilometers across, so an extra like 1 or 2, not going to make a very big difference. Cool. So the radius is, for all intents and purposes, constant. The mass of the Earth is, for all intents and purposes, constant, right? Because I mean, yeah, there's the odd little bit of space debris coming and leaving and stuff like that, but realistically, the mass of the Earth isn't changing. So that means this whole part is 100% constant, right? The g is a constant by definition. It's called our gravitational constant. The mass of the Earth is constant. The radius of the Earth is constant. Hey, any guesses what you're going to get if you were to actually go through and calculate this? So this little section, g times the mass of the Earth divided by the radius of the Earth squared. If you were to calculate this, you end up with about 9.8 meters per second squared, or about 9.8 newtons per kilogram. And that number should be very, very familiar to you. So anyways, I'm rambling a little bit here. First way is to use Newton's universal law of gravitation. Again, we've kind of already talked about, if we wanted to do this over and over and over again for stuff on the surface of the Earth, all of this is constant. Everything you see in the circle is, for all intents and purposes, constant, which actually means that we can make our next equation, right? So we've dealt with this equation since grade 10. Force of gravity is equal to mass times, maybe even since grade 9 to be honest. Force of gravity is equal to mass times the acceleration due to gravity, or more specifically, force of gravity is equal to mass times the gravitational field strength at a particular location. Let's go back a little bit here. We already said if we were to calculate this, so all of the stuff that's in the circle, it's going to be equal to about 9.8 newtons per kilogram if we're talking about the Earth. What's 9.8 newtons per kilogram? Well, that is our gravitational field strength on the surface of the Earth. So if I bring everything down, I've got my force of gravity is equal to G times M. Now that's written a little bit backwards than we usually do, but you get the same idea. That's where this comes from. And that also leads us to our new formula. Gravitational field strength is equal to the gravitational constant times the mass divided by the radius squared. Cool, so that's kind of what we're digging into today. Okay, so gravitational field strength, that's lowercase g. It has two different interpretations. It's got the weight per unit mass and the acceleration in free fall. So the weight per unit mass, this one's fairly straightforward, right? So I got g, gravity is equal to force of gravity divided by mass. Well, if I'm thinking about my units for that, it is my newtons per kilogram, and that's where that comes from. And what that realistically means is how much weight you have, so your force of gravity, for every 1 unit of mass. So for example, 9.81 newtons for every 1 kilogram. Perfect. That doesn't necessarily mean that anything is there when we're talking about that. Like, just picture the space in front of you. There's not necessarily anything there. But if something was there, we know that its force would be 9.81 newtons for every 1 kilogram of mass. If it was 2 kilograms of mass, it would be, let's see, what is that? 9 times 2 is 18, so I think it'd be 19.62 newtons per 2 kilograms. Cool. Now, the other thing to kind of note here is that G has a direct relationship with Fg. So in other words, if we double the gravitational field, we double the gravitational force, right? We triple the field, we triple the force. Cool. The other thing that we can look at is the acceleration due to gravity in free fall. We know that the net force is the sum of all the forces. So if it's in free fall, the only force that we have acting on the object is our force of gravity. So F net is equal to Fg. We can expand on each of these. M times A is equal to M times G. And then I rearrange and solve for A. So divide both sides of the equation by mass. Oh no, look at that. Acceleration is the gravitational field strength only if there's no other forces present. As soon as you add another force like air resistance, no longer the case. But it is a pretty good estimate for things that are moving relatively slow. Cool. So, two possible interpretations for gravitational field strength. So generally, we have newtons per kilogram, the weight per unit mass, but in free fall, we've also got it as our acceleration due to gravity measured in meters per second squared. Awesome. So let's just think about this for a second. I've got planet A. I've got a gravitational field strength of 2 newtons per kilogram. I've got planet B. I've got a gravitational field strength of 16 newtons per kilogram. And then, of course, we've got what we're used to, Earth, 9.81 newtons per kilogram. So how would you feel on planet A? Right? So essentially what we've said G is directly proportional to the force of gravity. Well, we decreased the gravitational field compared to Earth by quite a bit. So we decrease the gravitational force. You'd feel a lot lighter, like you've got less weight or less gravitational force. What about planet B? Same idea. If it's directly proportional, we increase the gravitational field strength. We would increase our force of gravity. We'd feel heavier. One last step that we could really take with this is how much heavier would we feel on planet B than on planet A? Well, let's see, it's 8 times larger of a gravitational field strength, so it would be 8 times heavier that we would feel. Pretty cool. Okay, let's jump into a quick example here. Okay, let's try and figure this one out. We got the surface of planet X. You know what that tells me? Tells me it's not Earth, so G is not 9.81 meters per second squared, or newtons per kilogram. Anytime we're on a different planet, it is not 9.81. Anytime we're not even on the surface of our own planet, it's not 9.81. Okay, anyways, rambling about that. So on the surface of planet X, we've got a 700-gram object. Okay, so that's going to be our mass. And it says it has a weight of 4.1 newtons. I should recognize that weight is actually force of gravity. It says this object is thrown straight upwards at 28 meters per second. And we want to determine its maximum height. Okay, what is this starting to sound like for people? So thrown upwards with an initial speed. We're looking to determine its maximum height. So it's maximum height where there's no speed. This is starting to sound like we could do this in one of two ways. We could do this using kinematics, or we could possibly use energetics for this. Either way, so let's just kind of think about this. We'll plan it out a little bit. If we're using kinematics, we know VI, we know VF, we're looking for the maximum height, so we're looking for D. So I think all the information we're explicitly given sure would be helpful if we had the acceleration due to gravity, right? If we're dealing with energy, so energy is all about ETI equals ETF, well, we're starting at the bottom, and we're starting with kinetic. And then we're going up to our highest point, or maximum height. The maximum height, there's no more kinetic. It's all been changed into gravitational potential. Cool. Okay, so 0.5 mvi squared is equal to mgh. I don't actually even need the mass for this one. But what I do need is g. So either way, if we're using kinematics or we're using energy, we need to solve for the gravitational field strength or the acceleration due to gravity. So I think that's our first step here. Find g. So let's see, we're given the mass and we're given the force of gravity. Force of gravity is equal to mass times gravity, so that's good. I think we can find the mass from this, no problem. Mass is equal to force of gravity divided by g. Oh, no, wait, hold on. That's not what I'm looking for. That's a different question I'm thinking of. We're looking for g in this case. G is equal to force of gravity divided by mass. That's going to make a little bit more sense. So let's see, 0.7. I am losing my marbles here. It is 4.1 newtons, and it is 0.7 kilograms. There we go. So 4.1, and hey, that's going to give us that unit that we like. So let's take a moment, let's plug that one in, and we're going to end up with newtons per kilogram. I end up with 5.857. 5.857 newtons per kilogram. Nice, okay. Not so bad, not so bad. Now that we've got the acceleration due to gravity, or the gravitational field strength, I'm gonna get you to put it on pause here, and you can try out either kinematics or energetics. I'm gonna choose one or the other. You put it on pause, you choose it. Our answers should work out to be the same thing either way, but go ahead and put it on pause right now. So kinematics or energy, go. All right, nice. I think I'm going to choose kinematics. So I know that I've got VI, and don't forget with kinematics, oh, it's all about vectors. So I'm going to have to say up is positive for kinematics. So I got positive 28 meters per second. I've got, let's see, VF is going to be equal to 0. I've got the acceleration is equal to the acceleration due to gravity, or the gravitational field strength. It's going to be 5.857 newtons per kilogram, or in this case, you know, it actually work a little bit better because we're talking about it in terms of its acceleration and freefall, meters per second squared. Nice. The only thing I really got to keep in mind with this is it's going to be downwards towards the planet. So I'm going to put a little negative in there, and then D is going to give me my maximum height, so that's my question mark. So kinematics, the reason I'm choosing kinematics, by the way, is because it's been so long for some of us, right? It's all the way back to Unit 1. So let's see, we've got our variable list. We have to pick a formula now. What's noticeably missing from the formula? Time, I think. Time is missing. So let's pick a formula that has obviously what we're looking for, but does not have time. So it has distance, but does not have time. The one that I found, VF squared is equal to VI squared plus 2A D, although I somehow managed to forget the A. Cool, so I want to rearrange this. I'm going to start by subtracting VI squared, so it's going to be VF squared minus, hold on, minus VI squared. Awesome. And then I'm going to divide by 2a, so divide both sides of the equation by 2a. And let's see, d, so our vertical displacement is equal to vf squared minus vi squared over 2a. So that's going to be 0. I don't necessarily know if we need to square that, but I'll put it there anyways. Minus 28 meters per second squared. And then divided by 2, and also divided by negative 5.857 meters per second squared. Notice squared's in the brackets. In this case, it's part of the unit. And yeah, I go ahead, we plug in some numbers. Let's see, you could do the same right now. You can put it on pause if you need to. Crunch the old numbers. I'm ending up with 67 meters, and that should be a positive 67 meters, which realistically the height is just 67 meters, but we get the idea. Cool. Could we have done this with energy? Let's just, I'm going to do this as a quick note off to the side. So let's see, we're looking for the height. The height's going to be equal to 0.5 VI squared divided by G. Can we see how that's the same equation? It looks a little different, but it's essentially the same equation. You can, if you don't trust me, plug it in, see what you end up with. Okay, so that's a bit of space for me to work. Now, actually getting into gravitational fields, like I guess we should have a kind of a definition on what a field is. It's a sphere of influence, right? And we can have gravitational fields. Well, it's the sphere of influence. It's a mass where that could influence other masses. So here's the Earth and a satellite, and its gravitational field is actually represented by this kind of weird meshy pattern. That's something you'll learn in later physics courses if you choose to take them. That's more dealing with Einstein and his theories of relativity. But yeah, so it extends outwards in space. So obviously, Earth's creating a gravitational field, and its gravitational field is affecting the satellite. But it could also affect anything that's out there in the middle of space. Even if there's nothing there, we could still describe that gravitational field as how it could affect other things. So sphere of influence. Nice. When we're drawing gravitational fields, so we typically want our central mass, that's our big mass that is creating that one, so we usually put that as a capital M, because this is the thing that is creating the gravitational field. Now, gravitational fields, they are indeed vectors, so we need arrows to represent them. So if I put something way out here in space at point X, I'm not saying that there is anything there, but which direction would it want to go? Right? So a mass is always attracted to another mass, so no matter where you put that, it would go towards that large central mass. Now, one little problem with this is that these lines realistically extend out into space forever and ever and ever. So, well, theoretically extend into space forever and ever and ever. Realistically, you get to a point where the gravitational field is so small you would never ever be able to experience it. But anyways, let's get back to it. If those lines could go on forever and ever and ever, we can't really treat gravitational field the same way that we treat normal vectors. So I might have 5 units for a normal vector here. If I wanted my next vector to be twice as big, I'd need to make the arrow twice as long. Can't really do that here because the arrows are infinitely long. So what we do is we talk about how tightly packed those arrows are. So let me clean up that. It wasn't a very good X in the first place. So if I had location X versus location Y, which one would have a larger gravitational field? Well, clearly X, one, it's closer, and that's, you know, when we look at our formula, obviously the radius has an inverse relationship, so the smaller the radius, the bigger the gravitational field strength. But on our diagram, those lines are just that much closer, which means it's that much stronger. Where at Y, the lines are significantly further apart, which means we're going to have significantly less gravitational field. So it's all about the density of how closely those lines are packed. Cool. Gravitational field strength, I already wrote this formula out. Just big things to know is this is the mass that is creating the gravitational field, and our radius is the radius from the center of that mass out to some random point in space. So there might not necessarily be anything there, but it's out some random point in place. It doesn't matter if there's a mass in the field, like if there's a mass out here, or if there's not a mass, not mass. It doesn't matter whatsoever, right? The gravitational field at that point would be the same either way. Cool. Okay, so here's a thought here. We know that it's the density of the lines, or how tightly packed those lines are, that give us our gravitational field strength. So what would the gravitational field diagram look like for planet A versus planet B, going back to these two? If you're thinking to yourself, should be a lot less lines and less densely packed for planet A. You're absolutely right. An interpretation might look something like this. So anywhere you go around planet A, so at the same radius, at spot X on planet A and spot X on planet B, well, B's got more densely packed lines, it's going to have a stronger field. Cool, okay. Hopefully we get the point on that one. Okay, one more example to go through here. So how far above the surface of the Earth would the gravitational field strength be? 5.8 newtons per kilogram. So some things to think about with this one. We are still absolutely talking about the Earth, but we're no longer talking about the surface of the Earth. So this is how far above the surface. This might be like on a satellite or on a spaceship or something like that, or just on any random point way above the surface of the Earth. Now, this doesn't look like this question gives us a ton of information, does it? It really, really doesn't look like it gives us a ton of information. So it's asking us for the radius, sort of. We'll talk about that more in a second. And it's giving us the gravitational field strength. On our data sheet, could we find the mass of the Earth and the radius of the Earth on our data sheet? Check it out. Have a quick look. Yeah, so the mass of the Earth, we find out is 5.98 times 10 to the power of, whoops, 10, that is just messy. Let me start over again. 10 to the power of 24 kilograms. Make sure you can find that. And then the radius of the Earth is 6.37 times 10 to the power of 6 meters. So again, take a moment to make sure that you can find those. We have those two pieces of information. Now you might be thinking to yourself, well, why is it asking us for how far above the surface? Isn't that got something to do with the radius? You're absolutely right. I think a diagram will help us out with this. So here's the Earth, and here is the capital R there, so I'll use capital R over here. Here's the radius of the Earth. The question is, how far above the surface of the Earth? So there's the surface of the Earth. This, the distance above the surface of the Earth, is our question mark. So the orbital radius, or the radius that shows up in our formula, just put that around kind of like that. I'm going to call it RO for the orbital radius, is from the center of Earth all the way up to that point in space. That's going to help us out quite a bit more when we're trying to find the distance, right? And you could probably already see it's going to be the orbital radius minus the radius of the Earth. Orbital radius, again, being from the center up to that point in space. So first things first, let's do our best to figure out that orbital radius. So we've got our gravitational field strength. We're looking for the orbital radius, so I'm just going to go ahead and rearrange. Orbital radius is going to be equal to capital G times the mass of the Earth divided by lowercase g. And then I think I want to square root that. So make sure you're good to go with that rearranging. You can take a second and check it out and make sure you understood what we did there. Let's go ahead and plug some numbers in. So the orbital radius is going to be capital G, so that's 6.67 times 10 to the negative 34. Oh no, you know what? You know what I'm doing? I'm confusing constants from physics 30 with what we've got here. So this is 10 to the negative 11. And you know what? You're going to end up with, by the time you're done physics 30, a ton of these 6 point whatever times 10 to the negative whatevers. If you don't know, just check. It's super easy. Newtons meters squared over kilograms squared. Okay, now that I've got that right, the mass of the Earth, 5.98 times 10 to the power of 24 kilograms. And then we're going to divide that by G. That told us in the question, 5.8 newtons per kilogram. And then don't forget, we need to take the square root of the whole entire thing. And again, take a moment to plug some numbers in. We end up with 8.293 times 10 to the power of, where was it there? Where are we? 6 meters. Okay, now again, this is not our final answer. This is our orbital radius, which we can see. I'll even highlight in a different color over here. This is my orbital radius from the center of the Earth all the way out to this point in space. If I wanted to go ahead and find my distance above the surface of the Earth, I could just say my distance above the surface of the Earth is equal to the orbital radius minus the radius of the Earth itself. Well, that's fairly easy math. 8.293 times 10 to the power of 6 meters minus 6 point, and it's another one that I got to double check here, 6.37 times 10 to the power of 6 meters. We plug those numbers in, and we should end up with 1.92 times 10 to the power of 6 meters. Excellent. 1.92 times 10 to the power of 6 meters. Or, in other words, I think that's 1,920 kilometers. That's, or sorry, let me do that one more time. 1.92 times 10 to the power of 6 divided by 1,000. Having a tough day here. 1,920 kilometers above the surface of the Earth. So definitely not on the surface of the Earth. Cool. So, I got my work done for myself here. Excellent. So, another lesson under our belts, folks. One thing that you may notice a little bit here as you go through is just the combination of, like we saw in that first example, the combination of energetics, the combination of kinematics. So make sure that you're looking back at some of those other units because those things don't really go away. Anyways, that is it for now. Good talking with you. We'll see you again soon, Physics 20s. Bye for now.